Hi, everyone. Thanks for being here. I'm going to tell you about Ray, which is a project we've been working on. A bunch of us in the lab have been developing, along with a number of people outside of Berkeley. So before I elaborate on the motivation for Ray, I want to say what we're trying to build. So we're working toward building an underlying distributed system that's capable of supporting all of the different components of the machine learning ecosystem as libraries and applications on top. So here, Ray is the blue underlying distributed system, and these yellow boxes are the libraries that we're also working on building. So that's what we're working toward and what we're building. Here's a depiction of the machine learning ecosystem today. We have a bunch of important computational patterns that appear. We often think about distributed training and reinforcement learning and training workloads like that in particular. But of course, training is one part of a broader ecosystem that also includes things like model serving, hyperparameter search, and various forms of data ingest and processing. And today, each of these components of the machine learning ecosystem is implemented as a standalone distributed system. So here are some examples of specific systems that people use to implement these different computational patterns. So you may use Horovod for training and Clipper for serving and things like that. And these are very powerful systems, but they're also very specialized. And this poses a challenge for cross-cutting applications that need to integrate many different computational patterns into the same application. And we're seeing that with a lot of new AI applications, a lot of reinforcement learning applications. We often want to do training and serving, run simulations, and streaming all in a single application. And so that's why we're trying to move from this paradigm to this paradigm, where we have a single underlying distributed system that's capable of supporting all of the other patterns as libraries on top. And of course, it's great to be able to do all of these things individually, but the real potential, the real benefit comes from enabling cross-cutting applications that integrate many of these boxes together. So now I'll say a little bit about the different levels in the Ray stack. At the highest level of abstraction, we have libraries that we're building. Some of these are more mature, and you'll hear about the Tune library and the RLlib library, and also Modin for data processing. But these are actually all of these libraries have very diverse computational patterns and very different distributed systems requirements. So underneath, we have to have a very general purpose programming model that's capable of expressing all of these different workloads. And the way we achieve this generality is through two core abstractions. So in regular programming on your laptop, functions and classes are two core concepts that you use to implement a lot of different workloads. And we're taking these two concepts and providing a way to translate them into the distributed setting. So tasks or functions map into stateless tasks, and stateful classes map onto stateful actors. And I'll elaborate about how this works and how you can use these things in a few slides. But we'll also go over these in more depth in the tutorial, and you'll get a chance to actually work with these. So this is the programming model, and you can also use this Ray API directly to implement various workloads in addition to using the libraries. So underneath this programming model, we have a backend based on dynamic task graphs, and this is what enables the performance of all of our libraries on top. So the backend reasons about a graph of task dependencies, and it handles functionality like scheduling, resource management, fault tolerance, data transfer, and all of these things. So these are the different levels of abstraction that we are thinking about. And now I'll talk a little bit more about the API and how you can use that to implement applications. So here are two Python functions. One of them just creates an array of zeros, and one of them multiplies two arrays together. Ray allows us to decorate these functions with the ray.remote decorator. And now if I invoke one of these functions, here I'm invoking the zeros function, that immediately returns a future, and it creates a task that is executed asynchronously in the background. Because it returns a future, I can immediately invoke the function again, or another function, to create a second task before the first one finishes. And that's how futures enable parallelism. So now I can take these two futures and pass them as an argument into a third task. That creates a dependence of the third task on the first two tasks. So you'll notice that the actual Python code that's being executed looks like regular Python. It's a straightforward translation from single-threaded Python. But it encodes these dependencies and these task dependencies that the backend can use to reason about scheduling and recovery from failures. And so the right-hand side is a depiction of the data structure, the task graph that the backend reasons about. And you can see that the two zeros tasks, the first two tasks can execute in parallel, but the third task can't execute until the first two have finished. And when it does execute, the outputs of the first two tasks will be shipped to where the third task is being executed. If we want to retrieve the output of these of the computation, we can call ray.get to do so. So if you're familiar with composable futures, this is a very powerful abstraction, and it can already express a lot of workloads. But one thing that it doesn't allow is it does not enable stateful or mutable objects to be shared and mutated by multiple tasks. Here, these tasks operate and output immutable data, which simplifies reasoning about failure recovery. But it turns out that mutable objects and stateful computation are actually really important for many machine learning workloads. And that can come up whether it's the state of a simulator that you're using for reinforcement learning, the weights of a neural network, or some other encapsulation of some interaction with the real world. So the way that we encapsulate mutable state and share it between tasks is through an actor abstraction. Here's a Python class, and it has a value, and it has a method for incrementing that value. Like before, we can decorate it with the ray.remote decorator. And now if we create an instance of this class, that creates a new actor process somewhere in the cluster, which manages and maintains the actor's mutable state. And then method invocations on that actor handle turn into tasks that execute on the actor process, and they return futures like before. And like before, you can retrieve the values of these futures by calling ray.get. So this is just the simplest possible example. We've invoked two methods on the actor, and these two tasks share and mutate the state of the actor by incrementing the value. This is just a simple example, but you can use this kind of API to implement fairly sophisticated applications that involve starting a parameter server as an actor and starting multiple workers as either tasks or actors and having them communicate with each other to get the latest parameters and update the parameters and all of these things. And actually, I'll show you what that looks like in a Python interpreter. So here is, I'm using Python on my laptop, and I'm typing ray.init to start the ray processes. This is essentially starting a scheduler and an object store. I'll go over the architecture in a minute. If you were running on a large cluster instead of on your laptop, this is the only line that would be different. Okay, so like we discussed, I'm going to import a few things. A parameter server can be implemented as a Python class, and it essentially, if you're familiar with the parameter server terminology, it's essentially a key value store where the values are the weights of a machine learning model, or the parameters of a machine learning model. That could be the coefficients of a linear model, or the weights of a convolutional neural network, or something like that. And it has two basic methods. It has an API that allows you to get the latest parameters and update the latest parameters. And that turns out to be enough to implement a lot of distributed training applications. So here we're going to give the parameter server, we're going to initialize it to have just a bunch of zeros as its starting parameters. And we're going to give it a method which updates the parameters, which returns the current parameters just by returning self.params. And we're going to have a method for updating the parameters. And in this case, it's going to take some sort of gradient update and just add that vector to the current parameters. So now with Ray, so this is just a Python class. If I decorate it with the ray.remote decorator, and now I instantiate one of these objects, that's going to create a new process somewhere in the cluster which has a copy of this object. And now through this handle, this PS object, I can invoke methods like getParams. So these methods, this method returns a future. And if I want to get the values, I can call ray.get. So I can, every time I call ps.getParams.remote, that's creating a task that runs on this new process we started up, and then ray.get is retrieving the actual value. We can see that if we update the parameters and pass in, say, a vector of ones, and then get the values again, now it's an array of ones. So this is nothing too complicated going on here. We're just showing how we can invoke methods on the parameter server actor. So now we can do something more interesting, which is to start some worker processes that actually do distributed training. So here we can define a worker as a Python function, or Ray remote function, and it takes in a handle to the parameter server. And then what the worker does in this application is it essentially just loops around and does three things. It first gets the latest parameters by calling the parameter server method. And then it computes a gradient update. And this is normally, in a real application, this is where you would use TensorFlow and you would use some data that you have locally to actually compute the gradient update. But for right now, I'm just going to make up a pretend gradient. And we'll sleep for a small amount of time to illustrate it. And then we need to take that gradient update and essentially send the update back to the parameter server. OK, so now I can actually start one of these worker tasks and maybe start another and pass in a handle to the parameter server. And now if I go back and actually get the parameters, you can see that they're updating in the background. So what we've done here is with a few lines of code, we've started a parameter server process that exposes an API for getting and updating parameters. And we've started some worker processes or tasks that loop around, communicate with the parameter server to get the parameters and update the parameters. And this is the anatomy of an example distributed training procedure. So the interesting thing here is that a parameter server, if we go back to these slides, a parameter server is something that's typically implemented as a standalone distributed system. OK, I'm going to just exit from this now. A parameter server is something that's implemented and shipped as a standalone system, kind of like a database. But by enabling us to implement the parameter server as a simple library or a simple application, it becomes much more configurable. For instance, if you want to change the parameter update rule, or if you want to switch from synchronous to asynchronous training, or handle stragglers differently, or wire up the communication differently, those are all a few lines that you would change in your application. Whereas if it's baked into how the system was built, that can be more challenging. So that's an example of something that we're pretty excited about. OK. So now I'll tell you a little bit about the architecture that enables this programming model and this performance. So here's a depiction of a cluster with 3 machines. And on each machine, we have some worker processes, which are Python processes. And you can have one or more driver processes, which essentially run the application. And on each machine, there's an object store. Whenever a task executes or an actor method executes, its return values are stored in a shared memory object store. And that allows all the workers and drivers to read the same objects using shared memory to avoid extra copies and unnecessary serialization of the data. There's a lot more to say about this process in particular, but it's something that is being developed in collaboration with the Apache Arrow project, and it's an important performance optimization. We also have an object manager on each machine and a scheduler on each machine. And the object manager is responsible for streaming objects between machines. The scheduler is responsible for assigning tasks to workers or assigning or giving tasks to other schedulers. We use a distributed scheduler in order to essentially have higher task throughput. On top of all this, there's a global control store, which is essentially a sharded database, sharded in-memory database that stores the task lineage, essentially specifications of the tasks that have executed, metadata about which objects live where. And this is important for essentially taking a lot of the critical state out of all the other processes and centralizing it logically. So this enables like the scheduler, the object manager to all be essentially stateless. So if one of them dies, you can simply restart it without losing anything important. And it also is nice to have all this state in a single place because then you can query it at runtime or afterwards to inspect what's going on. All right. One project I want to highlight is Modin, which is, if you're familiar with the pandas library for data frames and data analytics in Python, pandas is very widely used and very popular for data analytics, but it's one common complaint about pandas is that it's very slow. And so we're working on a project that speeds up pandas but preserves the exact same API. And what this allows is it allows you to take your pandas applications and simply change just the import statement, just change one line in order to speed them up. And there's an exercise in the tutorials that will illustrate how to do this. So right now we have sort of two different categories of data frame libraries. We have libraries that work really well for data analytics on your laptop and ones that work really well at a very large scale. And Modin is bridging the gap here, trying to enable something that works seamlessly in both of these scenarios. So something that can work well on a large multi-core machine or a laptop, as well as on a large cluster. Okay, and you'll see more about this in the tutorial, but it's easy to install, and it's just one line to change if you're already a pandas user. So Ray is an open source project. We're developing it on GitHub. Since our initial release last May, we've had a growing number of contributors and also have had a number of other releases. So we're working on 0.6 right now. And we have a growing number of use cases at companies as well. So I'll conclude by reiterating that one of the goals of Ray is to provide a unified distributed system that can support all of the different components and interesting computational patterns that appear in machine learning workloads. And it's a general purpose system for parallel and distributed Python. And we're developing it as an open source project. All right, so now we're going to transition to the tutorial section of the Ray presentation. So everyone should go to this URL. There are going to be volunteers who are walking around who have the password that you use to log in at this webpage. So they should be passing out give them a minute, they're coming around. But you're going to use your email address and a password that's being handed out right now. And then we're going to work through, mostly on our own, work through different exercises involving the core Ray API and how to use tasks and actors. All right, I'll give the volunteers a minute to wander around. In the meantime, while they're walking around, does anyone have any questions I can answer? Yeah. Mm-hmm. Yeah. So the question is, if you're already using PySpark, what implications does that have for how you would use Ray? Essentially, can you directly use your PySpark code or something like that? So you won't be able to directly run your PySpark application on the Ray runtime. However, one of the design goals that we're working on is to make it very easy to take serial Python code and translate that to the distributed setting with minimal modifications. So if you're starting with a serial version of your application, then it should be fairly minimal to modify to run on Ray. But the PySpark API is fairly different from what we're providing. Can you raise your hand if you've successfully gone to this web page and logged in? Okay. Can you raise your hand if you have not? Okay. So maybe people could wander around and help the people, or ask the person you're sitting next to. If you have a corporate VPN, maybe try disabling it. Try like make sure you typed HTTPS. Any other problems that people might run into? Let's see. Can you keep your hand raised if you're still not at this web page and not logged in? Yeah. So the question is, what kind of cluster environments can you run Ray on? So you were asking about things like Yarn or Mesos or Kubernetes. So people have used Ray on Yarn, on Kubernetes, and on Slurm, to my knowledge. I haven't done that personally, but you essentially, to get it working in these settings, you have to write, you don't have to do too much. It should work. But we have a pretty extensive documentation on how to use Ray on clusters, and it is generally compatible with these environments. Yeah. Yeah, so the question is there any notion of having jobs local to where certain data sets are, or where certain data is? So we have a notion of locality for both the data locality and also resource constraints. So that's at the level of tasks and actors as opposed to at the level of jobs. But if you have a data set, so we provide built-in support for specifying resource requirements of different tasks. That could be things like CPUs and GPUs, but it also supports arbitrary custom resources. So if there's a data set that lives on one machine, that machine can essentially have a label that says it has this data set as a resource, and then certain tasks can require that resource. And that would force those tasks to be executed on that machine. So that's one thing that's related to what you said. Yeah. Sorry? So is Ray able to auto-scale with resources? Yeah, so as a Ray cluster is running, you can add new nodes to the cluster or remove nodes from the cluster, and that will, and currently running jobs will be able to just automatically use those. We also have an auto-scaler that creates and scales clusters both out of the box on AWS and Google Cloud Platform, and that can be adapted for other cluster backends as well. Yeah. Yeah.
Can you say a little bit about how does it control the access of the shared state access?
So how does it, I see, how do we control access to state that's shared by multiple tasks? So actors execute tasks serially, so to avoid race conditions between multiple tasks executing at the same time. Does that answer your question? So in the parameter server example, even though you have multiple clients that are all invoking methods on the parameter server, those methods will be executed one at a time. If that doesn't answer your question, we can discuss it offline. Can you raise your hand if you're still having trouble logging in here? Okay, so there's somebody over here. Can someone, and someone over in the middle over there that could use help? And someone in back there as well. So and 4 people, and someone here also. If you could keep your hand raised just so people can find you, that would be great. All right, so to get started with the tutorial, let's see. So when you go to this, when you've logged in successfully, you should see a web page that looks like this. If you click on the Ray, let's see. Oh, I'm already logged in. But if you click on the Ray, you should click on the Ray link, and that should take you to a page that looks something like this. There are a number of different exercises here. So the ones I want to focus on are exercises 1 through 12. And there's also, if you look at the notebook, Accelerate Pandas. That is the exercise on Modin and speeding up Pandas workloads that I was referring to. So I would start with that, and that one can be done independently of the others in any order. And beyond that, I would start with exercise 1 and work through them in order. So each notebook should be fairly self-contained and have all the information needed to run the exercises in that notebook, as well as links to relevant documentation. But basically, the way this works, if you've used Jupyter before, there are a bunch of cells, and you can run these cells. And some of the cells have checks in them, so if things are not working, if you haven't done the exercises properly yet, then some of the cells will raise an exception. And so here this says at the bottom, there's an assertion error. It took 4 seconds, and this is too slow. Philip, there's still more people. So when things are not working, you'll need to go back to the actual exercises, which are highlighted in bold, and actually modify the application to use Ray to parallelize things to speed up the application. And once you've done that successfully, all the assertions should pass. And if you have questions, raise your hand. People will be wandering around to help if there are questions about how to do the exercise. And definitely talk to the people next to you to ask questions as well, in case they know the answer. So to walk through the first exercise together, we'll do the first one together, and then most of the rest on your own. So the way this works is the first cell just imports Ray, and the second cell just starts Ray. So nothing needs to be changed there. The third cell has some slow function, which here we're just, all it's doing is sleeping. And because it's slow, and we're executing it multiple times, we want to do those executions in parallel. So the way that Ray enables this is you can turn it into a remote function by decorating it with the ray.remote decorator. And once you've done that, a few other things need to be changed. So there are a total of 3 things that need to be changed. First, you have to turn the function into a remote function with this decorator. And now, if you try executing the next cell, you'll see that you'll get an error saying remote functions cannot be called directly. So you have to invoke them with .remote. So we have to go to the invocation of slow function and change that to slow function.remote. And we actually, one question we get a lot is why add all of these .remote calls? Because it could just be slow. You could just call slow function directly. And one of the reasons is to make it explicit where remote tasks are being launched and where essentially where remote procedure calls are happening. Because what that does is it both makes it easier to read someone else's code and see where the parallelism is happening, as well as to search through the files to find the places where parallelism is being used. as well as if you're taking serial code and porting it to the distributed setting, it forces you to think about each step where parallelism may be happening and whether that's what you want or not. Okay, so now we can run it with the dot remote, and you'll see that this list of results is a list of object IDs, essentially a list of futures. And so what we've done here so far is we've launched these tasks which return futures, but we haven't actually retrieved the values yet. So we need to call ray.get to actually get the values. And so once we've done that, we can run the last box, and it should say that it succeeded and say how long it took. So that's the rough idea for the first exercise. I'd like everyone to go through that exercise and the subsequent exercises individually, and to please raise your hand if you have questions. Okay, thank you very much.